Okay, let's begin. We are going to jump right back into it. One more test to tell you about. Series convergence tests continued. What number are we on? Is it 10, 9? Huh? 9, we're on 9, so we know about 9 tests. 10 if you count the telescoping series, but that's not really a test, it's just like a calculation trick. The last test I want to talk about is something called the root test. And this one also has a convenient time to actually use it. Use when you have, especially when you have a series where your an looks like something to a power, like the power n. In particular, it's very nice to use this root test with. So here's how the root test works. You are going to set L equals to the nth root of the absolute value, just in case you have negative powers here. Of A. Then the following holds. If we want the limit. Of course, as n goes up to infinity. Now, if your L is less than 1, the series converges. In fact, it converges absolutely. If your L is larger than 1, the series diverges. And like the ratio test, if L equals 1, this test is inconclusive. Use something else. That's basically it. This is the root test. You take the nth root of something. And first take absolute values, so if it has negatives, you will kill them and look at the nth root of the thing that you want. And if that limit approaches to a value less than 1, it will converge. Let's give an example. You see a series that looks like this. It goes from 1 to infinity, up to n plus 7 over. Well, I didn't mean to write a 3, but I think that's going to work. Minus 2. And all of that is raised to the n. You have a series that looks like that. It's very nicely, you'll notice that you just have something that's very nicely raised to the nth power, or something similar to that. Now once you see something like that, it makes you think of the root test immediately, or it should. Of course, first thing you try to do is find the limit. You'll see that the limit goes to 0, so I can't use test for divergence. Other than that, now I'm going to think, what can I use here? Can I compare it to a P series? Can I do blah? Can I do blah? It's not geometric. But the fact that you have just some random expression raised to an n makes it nice for the root test. So let's say we employ the root test. Your L is going to be equal to the limit as n approaches infinity of the nth root of the absolute value of 2n plus 7 over 3n minus 2 to the n. Now, of course, what's going to happen here is this is going to cancel, and we're going to have the limit of that. What is that limit?
2/3.
2/3. Now 2/3 is less than 1. Therefore, you can say the series converges. In fact, it converges absolutely. By the root test. Meaning if you were to add up an infinite number of terms like this that look like that, they'll actually add up to some number, some finite number. Called root test. And that's, those are all the tests we wanted to do. Now, I am going to want to summarize things, and I'm going to also have you guys summarize some things, but in the meantime, just for fun, I wanted to throw out a couple problems. Do the following. Converge absolutely. Converge conditionally. Or diverge. So here to it. I might throw out another example, just for practice. Here's the first series. It goes from 1 to infinity. Cosine squared of n plus 1 over n squared plus 1. Second series. Minus 1 to the n cosine n factorial over n to the n. It goes from 1 to infinity. I want you guys to try that. Put your series muscles to the test. Might throw in another one. Pick up another nice example. Give you roughly 3 minutes per series. That should probably be enough. I think that's enough. Actually, try it. last one. So maybe I'll just pause here and have you guys do that. But guess at the same time, I can have you guys do another activity and then do this, and then we'll do it again. Because as you can see, I hear everyone flipping through your notes. He's flipping like that. So, what is a good idea to do is to have all the tests in one location. So here I made out some blank pages, and yes, I could have filled out the table for you, but I decided against it because I figured it would be a good exercise to make them work for it, you know, to like, when you have to fill out the table yourself, you're gonna remember it. So you can go through all these tests, and I would say do this first, fill out the table. I'll give you an extra 3 minutes for that, so we'll do like this. Maybe this whole thing will take like a 20-minute exercise. So you are going to write down all of these guys. So geometric series, you're going to say when to use the series, which means what are you going to look for that hints to you that that would be a good thing to use.
Could I have it?
And then you're going to write down the conclusion. So for example, look, I just did it, so that one should be fresh in your mind. So let me just do it. So for example, in the root test, so you're gonna have the root test, and in the when to use column, you would say something like, technically you can use it for any series, especially useful when you have an to the nth power, right? It's like something to the nth power, or however you want to actually state it. And then in the conclusion column, I would actually write down the test. L equals the limit of the square root of an, and if L less than 1 converges absolutely. L greater than 1 diverges, and L equal to 1, no conclusion, something like that, right? So you're going to fill out that. And the last column is just the section in the textbook, which look up that some other time, but actually just fill that out. So you're gonna, for each test, tell me when you would think of using it, what would hint to you that it's a good idea, and how would you actually know what the series tells you? How does it tell you about convergence or divergence? Fill that out in this column. Once you have this page filled out, so now all the tests are in one place, then I want you to go to here and actually do these problems. And then use your sheet to help you do the problems. So, yep, do that. And I'll make that a 20-minute exercise, and probably just to make sure it goes a little bit faster, you guys can pair up. And yeah, okay. Okay, well, let's begin. So hopefully you finished the table and got through these. Where are the guesses here? Which ones converge, diverge? How? First one. What do you think? Yeah?
I said converted conditionally.
Converges conditionally. Okay, what is your guess for this one?
Also, yes,
Converges conditionally. Okay, what about this one?
diverge.
Diverge. Okay, did you get here?
No.
Did anyone get to here? Does everyone agree? Is anyone confused? Okay. All right. Let's actually go through these. So tell me, what did you actually do for A?
The right comparison.
With?
1 over n squared.
Okay. So yeah, so that would say it converged, because then you would multiply 1 over n squared, the limit would be, okay, but so did you actually check absolute convergence or no? Do you even check?
I did that test.
Huh?
I just did that test and I found that equal 1. And since 1 over n squared converges at the, that means a n also converges, which is.
Yeah, but I mean, the way the question was phrased, converges absolutely, converges conditionally, or diverge. So there are 3 things you have to check. So you know it doesn't diverge because you got it converged, but that's conditionally. Why didn't you check absolutely? You just didn't do that, you just thought convergence? Okay, so when a question is phrased this way, absolute convergence should be the first thing you check. Should check absolute convergence first. Why? Because if absolute convergence works out, conditionally is definitely going to work out, so you don't have to worry about it. It's much harder to converge absolutely than to converge conditionally. Guys that converge absolutely automatically converge conditionally, but it doesn't go the other way around. If you converge conditionally and you check that, you might additionally have to do another test to check absolute. So it's usually best to check absolute first, because if that works, you don't need to do any other check. But if you went off and you check conditional and you get it works, now you have to, in addition to that, check absolute convergence. So absolute convergence is what I would look at first. So for A, I would look at the absolute value of that. Now looking at that, what can you tell me?
It's always positive.
Huh?
It's always positive.
Yeah, that's what the absolute value means. What else can you tell me in terms of its convergence? What do you think? What kind of test I can do here?
Ratio test?
Ratio test, that would be inconclusive. The big guy is here, the big guy here is the n squared. So you would have the n plus 1 all squared over the n squared. They're gonna behave the same. There is a cosine here. Can you tell me about cosine? Or the absolute value of cosine? Someone looks at cosine squared in absolute value. What can you tell me about it?
It exists from 0 to 1, that's it.
It's between 0 and 1. Yes.
Yeah.
That's true for any n. That's going to be definitely true. So what can you tell me about cosine plus 1 in absolute values? It's gonna be somewhere between 1 and 2. What do you think you can tell me about that? Right? What can you tell me about this guy? So for a second, imagine that that was your series. What would you be able to say?
One is definitely convergent.
That definitely converges. How do I know?
It's just going to infinity and then it's just in denominator, so it goes to 0.
Let me go into 0 doesn't mean convergence. Because if I had this, that does not converge. So let me go into 0 does not mean convergence. How do I know that that converges?
Is it P-series?
It's not exactly a p-series, but there seems to be an obvious one you'd want to compare it to, right?
Mm-hmm.
2 over n squared. How does this compare to that?
Mm. 2 over n squared is greater.
Huh?
2 over n squared is greater.
This one is bigger than that, and this one is a convergent p-series, right? Which means this converges, and if this converges, that means that converges by comparison. So you look at that, you realize that this is less than or equal to the sum of 2 over n squared plus 1. Then you're going to say that's less than or equal to the sum of 1 over n squared, which is a convergent p-series. Which means this guy with absolute values around him converges, which means he converges absolutely. That guy's absolutely convergent, not conditionally convergent. Even if I put absolute values around all the terms, he still converges. Very common trick. Again, that's something even from Calc 1 when you're doing limits you would check. You see a trig function like a cosine and a limit, you're probably going to want to throw absolute values around it, maybe use a squeeze theorem or something like that. The intuition behind series, a lot of it is actually falls in line with the intuition behind limits, even though a limit itself won't actually give you the answer. So I see a cosine, I'm going to think, well, the maximum that could be is 1. So the maximum of the top can be is 2. And so really when I look at this, it looks complicated, but I can just look at that instead. Right? That's going to give me an upper bound, and that allows me to use the comparison test. So by comparison test. So basically I compared this to that. That converges because it's a p-series, and so by comparison, this guy converges because he's smaller than something that converges. And he's also definitely larger than 0. So that's that one. What about B? What did you say it was? Yeah?
Do the ratio test.
The ratio test. So could you do ratio test? I mean, if you look at cosine of n plus 1 factorial over n plus 1 to the n plus 1, and you divide that by the cosine of n factorial over n to the n, what would that ratio approach? It's cosine of this, cosine of that. Technically that doesn't exist because your cosine is just going to keep bouncing up and down. They'll never actually settle anywhere. There'll be no way to determine what that actually goes to. So I probably don't want to deal with that limit. Other ideas?
Alternating test.
Alternating series test, good choice, but that would only check conditionally. How do I want to check absolute first? So look at the absolute first. The series of the absolute value of cosine of n factorial over n to the n. So forget absolute convergence. What else do you think? We'll check we'll check, you will use the alternating series test if this one doesn't work out. But maybe just thinking about the alternating series test can help you see something here. What do you think? You have an idea?
Well, I mean, if you just look at cosine of n factorial over n to the n,
Mm-hmm.
as that, like, that's just going to become, like, it starts at 1 and it's just going to get smaller and smaller. And cosine, if you're just looking at it from 1 going smaller, is a continuous function. So you can actually use the alternating series test to prove that.
Well, why not? What does that,
No,
as n gets larger, what is happening here?
as n gets larger, the bottom is wearing out, so
Yeah.
it's going to 0.
So the inside is going to 0. What does that mean?
That cosine would be going to, actually it would be increasing. Yeah, it'd be going
It'd be going to 1. The limit of cosine of n factorial over n to the n is actually equal to cosine of 0, which is 1. In particular, that's not 0. What does that mean?
1.
Divergence. Test for divergence. The limit doesn't go to 0. Test for divergence is one of the first things you look for. I haven't looked for it here, but it's clear that this one actually went to 0 because the denominator was a square, the top was a cosine. There's no way the cosine is going to win. So that limit's going to go to 0, which is why I decided to jump in to check absolute convergence. This one though, especially just seeing the cosine there, I'm skeptical because I know cosine bounces up and down, so I'm like, the limit's probably not going to exist. But then upon closer inspection, I realized, oh, the angle is going to 0. The limit is actually going to 1, right? Which means off to infinity, we keep adding 1 over and over. And that's not going to converge if I keep adding 1 over and over. So this one actually diverges by the test for divergence. Okay, what about C? You also got that divergence. What did you see about this that diverges? So probably check absolute convergence first, so don't worry about the signs for now. What can you tell me about that guy? Why did you feel it diverges?
Can you use the root test?
The root test would be inconclusive, right? Because you take the nth root of this, you get rid of the nth power. What is the limit of n over n plus 1? That's 1. Root test is inconclusive. Other ideas? Who told me diverge? Jakob. Why did you say diverge? What did you do?
I did a ratio test.
Did the ratio test. You would also get 1 by the ratio test. I didn't mention that, but that's probably important for me to mention. Star. Ratio and root tests give similar results. Turns out they're very closely related in the sense that if one gives you an inconclusive result, the other one is going to give you an inconclusive result. So it's clear that the root test is inconclusive. It therefore means that the ratio test is automatically going to be inconclusive. look at the limit. What is happening to this? What does n over n plus 1 to the n approach?
You want?
1 to infinity.
1 to the infinity, what does that mean? It's indeterminate, how do I deal with it? Well, just because it gets me 1 to infinity, I'm not, the denominator is heading to 1, so I'm thinking it's not going to hit to 0. So I'm already thinking, yeah, this isn't going to work out for me, right? But still, it's indeterminate, so I do have to get a little bit more specific. So let's look at this limit. So y equals that limit, how do I find it? How do you compute that limit?
You have to change it into a form of infinity over infinity or 0.
How?
We should just do it.
With n over 1 over n plus 1.
Oh, you want to write it as n to the n over n plus 1 to the n? To get infinity over infinity? That's cool, but what is the derivative of n to the n? It's kind of messy. I mean, it's not. Take you a little while, but it's not messy. Which, probably the quickest way to find the derivative of n to the n, if you're going to go through that trouble, you might as well have done it with the original. Nth power is a problem. How do we deal with powers that are problems? Logs. Figure out a way to get logs in there. Log both sides. This is going to be the limit of ln of n plus 1 to the n, which I'm allowed to bring the n down. And that would be infinity times 0, but all I would do is rewrite this as ln of n over n plus 1 over 1 over n. That would approach 0 over 0. So I would apply L'Hopital's rule. My ln of y by L'Hopital's rule is going to be, what is this?
N plus 1
Well,
over n.
come again?
N plus 1 over n. On the, as the numerator.
Mm-hmm. Times the derivative of that.
N plus 1 minus n. Which
Are you
would
doing the
be
quotient rule?
1.
Bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared. The bottom minus 1 over n squared. What can you say about that? So here I have the limit of n plus 1 over n times n plus 1 squared times n squared negative. What happens now?
Cancel it out.
Hmm?
Oh, it's n, or negative n over n plus 1.
Sure. I mean, you could see something quicker though,
Oh,
but
yeah.
okay. Limit of negative n over n plus 1. What happens?
Negative
It's negative 1, right? Because I see it's a negative n cubed over n cubed. Limit's going to go to 1. So ln of y is equal to that, which means that our y is equal to e to the minus 1. That actually goes to 1 over e. In particular, not 0. That diverges. Here's another thing you could do. Notice that if I look at the limit of n over n plus 1 to the n, or I could have written this as 1 over n plus 1 over n to the n. Why would I do that? Well, this is 1 over, if I simplify the inside, that's going to be 1 plus 1 over n to the n. And 1 plus 1 over n to the n, as n goes to infinity, what is that? It's another way to write e, right? So you could have done that as well. So that guy, it's a very common thing to show up. That's why I said, oh, that's a nice one, because it shows up every now and then. You get e in this very weird way, or 1 over e. So at the end of the day, what this basically means is the series diverges. Test for divergence. Because the limit went to 0. It went to a non-zero number. So eventually, way off in infinity, we keep adding numbers that are as big as 1 over e. And so that's never going to converge. So this does diverge, but it doesn't diverge by the ratio test. The ratio test would be inconclusive. The root test is also inconclusive. But test for divergence, again, one of the first things I would check. Seeing that it goes to 1 to the infinity makes me think, limit is 0. Possible, unlikely. And when you're finding out that this is probably the way to go if you don't really see the trick, but a trick like this, from now on you should be able to see it. Let's look at D. Okay, so I don't think anyone got to this one, so maybe tell me right now, how would you think about it? So first look at it with absolute values, and of course we would have what would you look at that guy? What can you tell me about that guy? First thing you look for, test for divergence. Limit goes to 0, can't use it. What else? It's not geometric. It's not a p-series. Is there something I can compare it to? One thing I'd say, that radical is kind of annoying, but it's an annoyance I can get rid of, right? Because there's a log. So that's actually 1/2 ln of n plus 1. So that's really the guy I care about, n plus 1. What can you tell me about that guy? Yeah?
Could you use alternating series?
It's not alternating.
Oh. It's not alternating because of the absolute values, right?
Right. We're checking absolute convergence first, so there's no change in signs. So ln of n plus 1 is a real tough one. First of all, you should also notice that if you were to use the ratio test on that, that would be inconclusive. If you wanted to use the root test would also be inconclusive. One thing you'll also notice, that guy doesn't look nice. It's not something I can integrate easily, so I wouldn't use the integral test. It's not geometric, can't use the geometric series test. It's not a P series. It's not really anything. Alternating series test doesn't apply because I'm not changing signs. What other tests are there out there? By comparison. Comparison. Oh, there's an idea. Maybe there's something I can compare this to. The ln is really annoying. Can I compare it to something without an ln?
Why is the ratio test inconclusive?
Well, if I look at n plus 2 over 2 over n plus 1, and I look at that limit, what is that approach? There's not much difference between log of n plus 2 and n plus 1 as I'm going off to infinity. These two things grow with the same magnitude, limits going to 1. So, yeah, ln of n plus 1 versus ln of n plus 2, they're the same in terms of limits, so I know that's inconclusive. Can compare it to anything. Yeah.
So ln of n plus 1 will always be greater than 1.
No, I don't think that's true. Because when n is 1, you get log of 2. 2 is less than e. Log of e is where we hit 1. So I probably wouldn't think along those lines. There was an idea that you could, again, learn from limits about how different functions compare to each other. Logs versus polynomials versus exponentials versus factorials versus variable-based exponentials. You learn that these guys are bigger than those guys. Which means if you end up with an ln and there's nothing else around it to like, for you to do like an integral, because if there was another n here I could do the integral test, so there's nothing that would save me here, I would probably compare it to one of those other guys. In fact, I kind of realized that if I look at ln of n plus 1 and I compare that to say just n plus 1, what does this idea tell me? Well, n plus 1 is always going to be larger than ln of n plus 1. What does that mean for these two fractions?
That one's the log one's greater.
Huh?
The log one's greater.
This one's bigger. What can you do with that? What can you tell me about this guy? So focus on this guy for now. What can you tell me about that guy?
You can compare
Yeah?
Compare 1 over n.
You can compare it to 1 over n. In fact, it's equivalent to 1 over n. I can just do a shift. Because see, this one starts at a half, then a third, then blah, blah, blah. So it's kind of like I have 1 over k, but I started at 2. Right? So it's harmonic. So it's diverges. It's harmonic. What does that mean for the original? Diverges by comparison. So it does not converge absolutely. Does it converge conditionally? So now I threw absolute values around it, it doesn't work. Now the question is, if I remove the absolute values and try to get away with conditional convergence, does it work? So now I'm going to check conditional convergence. So I'm looking at this guy, minus 1 to the n over ln of the radical of n plus 1. Okay, without absolute values. Now what do you think? what would you do? Alternating series test. Notice that 1 over ln of n plus 1 is decreasing. Also notice that the limit of 1 over ln of n plus 1 is 0, which means converges by alternating series test. Which means, what is the final conclusion here?
Converges conditional.
Converges conditionally. The series converges conditionally. You guys need a lot of practice. Go home this weekend. You need to kill that series section. Look up the series chapter in the book. It's 11.3 through 11.7 or something like that. And I believe in 11.8 there's like a review section where it mixes a lot of different kinds of series. You want to practice actually looking for how to actually use that series. In regards to this, because I didn't want to take the risk of you guys writing down something wrong, I actually posted like a filled out one on the class website. So you print that out, and while you're doing your series, have this right beside you. Make sure you're trying to match things to the test that's going to work, and keep doing it until you have this table in your head memorized, and you can really kind of start to see, oh, I see, obviously I'm going to do this, obviously I'm going to do that. Yeah, so you'll pick up a lot of tricks. If there's a trig function, replace it with plus or minus 1 if it's a sine or a cosine. If I just see a log by itself, replace it with a polynomial. That's going to work out nicely. Little tricks like that you'll pick up after you do a few problems. So try to do that, and we'll pick up with that next time.